Welcome. Today, we are wrestling with a surprisingly tough customer, raw jute. We're going to get right into the nuts and bolts of jute carding, a process that is absolutely essential for turning this coarse, rugged plant into a usable textile. So, let's start with the big question, right? You've got this fiber that's incredibly strong, which is great, but it's also harsh and really stiff. You can't just feed it into a machine and expect yarn to come out. So how on earth do you tame it? Well, the solution, like in so many industrial processes, is all about some very clever engineering. It boils down to a two-stage mechanical process. And this process is designed to do two things. First, to make the fiber spinnable, and second, to clean out all the impurities. Okay, so here's our game plan. First, we're going to dig into why carding is even a thing. Then, we'll meet our two main players, the breaker card and the finisher card. After that, we'll put them head-to-head to see how they're different. And finally, we'll get into the nitty-gritty numbers that make this whole operation work. All right, let's kick things off with the fundamental issue. Why are we even talking about this? And more importantly, why do you need two machines? Understanding this is the key to grasping the entire process. So carding is basically a two-for-one deal. Job number one is to mechanically soften and untangle those stiff jute fibers so you can actually spin them. But at the exact same time, it's cleaning them up, getting rid of any plant debris or dirt. That's why you need two machines, one to do the rough, heavy-duty work, and the second one to do the delicate, refining work. Okay, let's meet our first machine, the breaker card. I want you to think of this as the brute force of the operation. Its whole purpose is to take that raw, messy jute and give it its first really aggressive breakdown. Now, before we see how it works, let's get familiar with the main components. You've got the parts that feed the fiber in, you've got this huge central cylinder that does most of the work, and then a whole team of specialized rollers, the worker, the stripper, and the doffer, that manage the fiber as it moves through. We'll see how they all work together in just a second. And here it is in action. This diagram shows you the whole journey. You can see the raw jute being fed in from the left. It immediately meets that giant pin-covered cylinder. From there, it gets passed up to the smaller worker and stripper rollers, which comb it out before it's collected by the doffer and then condensed into this thick rope of fiber called a sliver. So how does this actually work? Well, the whole secret is speed difference. The main cylinder is spinning incredibly fast, but the worker roller above it is moving much, much slower. As the fast-moving cylinder carries the jute fibers past the slow-moving worker, the pins basically comb or card the fibers, separating and aligning them. Then the stripper cleans off the worker, puts the fibers back on the main cylinder, and the journey continues. It's really quite brilliant. Okay, so the jute has had its first pass. It's been broken, but it's still pretty coarse. This is where step 2 comes in. That sliver from the breaker card now gets fed into the finisher card. And as the name suggests, this is where the real refining happens. And right off the bat, you can see this is a much more complex beast. Look at this. Instead of one worker and stripper set, you've got 4. Instead of one doffer, you have 2. All of this extra hardware points to one thing: a much more detailed, intensive, and precise process. This diagram really shows you that complexity. You can see this sliver being fed in, but now it has to go on a much longer journey around the cylinder, interacting with 4 different sets of those worker-stripper pairs. Then the web of fiber is actually split and collected by 2 different doffers. The goal here is pretty simple: thin it down and get those fibers even more individualized. The core principle is exactly the same, using those speed differences to create a combing action. But here, everything is turned up a notch. The space between the rollers is smaller, the density of the pins is higher, and having multiple stages of carding and doffing creates a sliver that is way finer and much more uniform. It's now ready for the next step. All right, now for what might be the most important part if you're studying this. Let's put these 2 machines side by side. Truly understanding the differences between the breaker and the finisher is absolutely critical. So let's start with the physical design. The breaker is what's called a half-circular machine. The finisher is full circular, which gives it more surface area for that carding action. We've already mentioned it. The breaker has 1 doffer, the finisher has 2. And, really important here, the pin density is much lower on the breaker. The finisher needs that higher pin density for its fine-toothed comb action. Now let's talk performance. This is where you see the trade-offs. The breaker has 1 worker stripper set. The finisher has 4. That directly affects how much material they can process. The breaker is a high-volume beast, churning through over 800 pounds an hour. The finisher is much slower, about half that, because its job is precision, not bulk. And that's reflected in the settings. The gaps between the rollers are wider on the breaker and much, much closer on the finisher. Okay, we've covered the what and the why. Now let's get quantitative and talk about the how much. These are the actual numbers and calculations that operators on the factory floor use to control the entire process. First, let's tackle this term clock length. It sounds a bit technical, but the concept is actually pretty straightforward. It's just the length of jute, measured in yards, that gets fed into the machine during one standard cycle. And that cycle is called a dollop. So if clock length tells you the input length, dollop weight tells you the input mass. It's simply the weight of that same dollop of jute. And this is where it gets useful. By dividing the weight by the length, you get the material's linear density. That calculation is how you ensure the final sliver coming out is the exact thickness you need it to be. And now we get to the heart of the mechanics. Speed. Just look at these numbers. The cylinder is absolutely flying at over 2,400 feet per minute, while the worker is just crawling along at maybe 40. That massive difference is what makes carding work. Now, for those of you studying this closely, I want you to notice something. The source material I was working from actually mislabeled this table. It called both columns breaker card. But if you analyze the numbers, you can see the second column has to be the finisher card. The worker speed is slightly lower, the doffer is slightly faster. It's a subtle but important distinction. Getting those details right is crucial. So when you put it all together, you realize this whole process is a massive balancing act. An operator can crank up the cylinder speed for more carding action, sure, but they risk damaging the fibers. They could speed up the worker, but that might cause breakage. Slowing the worker down preserves the fiber quality, but you lose production efficiency. It is a constant game of trade-offs between speed, quality, pin density, and the physical settings of the machine. And there you have it, a deep dive into the workhorses of jute processing. But this brings us to a final question about the future. For technology this fundamental, what's next? As textile science advances, what's going to drive the next evolution of carding machines? Is it going to be a raw need for more speed, a push for better energy efficiency, or will it be the challenge of adapting these incredible machines to handle brand new types of composite fibers? That's a question for the next generation of engineers to figure out.